In this video, we're going to take a look at hydrogen bonding. Hydrogen bonding is the strongest type of dipole-dipole interaction, and it occurs specifically between a hydrogen atom that's bound to an oxygen, nitrogen, or fluorine, and another oxygen, nitrogen, or fluorine atom. This may make a little more sense if we look at a few examples. Here we have HF, hydrogen fluoride, we have water, H2O, and we have ammonia, NH3, all demonstrating hydrogen bonding. It's the strong polarity of the hydrogen something else bond that allows hydrogen bonding to take place. The chi, or electronegativity difference, between hydrogen and fluorine is 1.9. That's nearly as high as the 2.0 we would use to classify an ionic bond. This is a very strong, very polar bond. Because of that, a lot of the electrons in that single bond are being pulled toward fluorine, which leaves that hydrogen high and dry. It's strongly positively charged because the fluorine is hogging the electrons so strongly. You can see that here in the electron density map. The hydrogen is strongly green, meaning it is strongly positive, and the fluorine is red, meaning that it is strongly negative and has a lot of electron density around it. The negatively charged end of one hydrogen fluoride molecule is attracted to that strongly positive hydrogen atom on another HF. You can see that here the lone pair on the fluorine is coordinating to the hydrogen. This is the hydrogen bond. Water does the same thing. The lone pairs on oxygen will attract a hydrogen from another water molecule as seen here, and the same thing happens with ammonia. The lone pair on nitrogen interacts with the hydrogen on another ammonia molecule. The more hydrogen bonds you can form, the more strongly it will feel intermolecular forces and the stronger the effect they will have. This is especially apparent in water. In liquid water, a single water molecule can form up to 4 different hydrogen bonds with 4 different water molecules. This dense hydrogen bonding network is why water has such a high boiling point and such a high surface tension. Its intermolecular forces are huge. You can also have a hydrogen bond take place between a conventional hydrogen bonder, like water, and the dipole on another molecule, like the carbon-oxygen double bond in this acetone molecule. Remember, hydrogen bonding stems from extremely polar oxygen, nitrogen, or fluorine bonds to hydrogen. The carbon-hydrogen bond only has a chi of 0.4, classifying it as nonpolar, and therefore it will not take part in hydrogen bonding. The last example I want to draw to your attention is DNA base pair binding. These 4 structures are nucleotide bases, and your DNA is made up of them. The adenine base only binds with the thymine base, and the guanine base only binds with the cytosine base, and this is because of the hydrogen bonding these pairs undergo. The adenine-thymine base pair has 2 hydrogen bonds that are carefully matched in their geometry so that they only can find each other in terms of orientation. And the same is true of the guanine cytosine with its 3 hydrogen bonds. And in each of these, you can see that the hydrogen bond consists of the NH bond coordinating to the C double bond O on another base. See you guys in class.